Hello and welcome to today's lesson on scalars and vectors, which is part of the forces topic in GCSE Separate Science Physics. So in today's lesson we're going to look at understanding what scalars and vectors are. So if we've been successful and learned in today's lesson, we should be able to describe the differences between scalar and vector quantities, add vector and scalar quantities, and finally draw vector diagrams for vectors where the size and the direction of the arrow represents the size and the direction of the vector. We're synced into the following part of the AQA GCSE Separate Science Physics Specification 4.5.1.1 Scalar and Vector Quantities. Now, scalars are quantities which only have a magnitude or a size associated with them, which can include things like mass, temperature, length, energy, time. Now, all these quantities have a magnitude, but they do not have a direction they act in. They just exist. Now, vectors are quantities which have a magnitude and a direction associated with them. This can include quantities such as weight, momentum, acceleration, force and velocity. Now all these quantities have a magnitude and a direction they especially act in. Now let's just clarify this. Scalars are quantities which only have a magnitude associated with them. Vectors are quantities which have a magnitude and a direction associated with them, and we've got to treat these concepts differently, both conceptually and mathematically. Now some quantities have a scalar and vector counterpart. So in these examples, the vector is the scalar with the direction added. So for example, speed is the scalar, velocity is the vector. So velocity is speed with the direction. The scalar is the distance travelled, the velocity is the displacement. So the displacement is the distance travelled in a particular direction. So vectors are scalar values with the direction included in their answer. Now the easiest way to add a direction is to place a plus or minus in front of the value. So plus 20 meters per second and minus 20 meters per second show that the object is moving in opposite directions. So it's very important because vectors contain more information than scalars. However, some quantities are just naturally scalar. So here's an object which has both scalar quantities and vector quantities. So how do we represent scalar quantities on objects, and how do we represent vector quantities on objects? Well, scalar quantities are represented by just a number and a unit, whilst vector quantities are represented by a number and a unit and an arrow showing their direction. So how can you tell that in this particular example the two vectors are different from each other, and what is that particular difference? Well, the vectors on 1 and 2 are different as vector 2 is larger than vector 1. You can see this because the length of the arrow shows the size of the vector, and vector 2 has a longer arrow than vector 1. What's a similarity between the two vectors shown in the diagram, and how can you tell it? Well, the similarity is that vectors 1 and 2 are both acting in the same direction because the direction of the arrow is pointed in the same direction, and that shows the direction of the vector. So the arrow describing the vector is very important as it shows the direction the vector acts in and the size of the vector. The length of the vector arrow must indicate the size of the quantity, and it must be in scale. So for example, we could say that 1 centimeter equals 1 Newton. Now you can actually decide the scale you want to use yourself. So scalars must be represented by a number value with a unit only, whilst vectors must be represented by a number value and an arrow. The direction of the arrow shows the direction of the vector, and the length of the arrow shows the size of the vector. Now adding two scalars is very simple. It's the standard addition which you've carried out all the way through school. So for example, what's the total volume if volume 1 is 10 centimeters cubed and volume 2 is 20 centimeters cubed? Well, you just got to add the two volumes together because they are scalars. Whilst adding two vectors together is more complicated, as you've got to consider the direction as well as the size. Now, like we mentioned before, in physics, opposite directions are considered as a negative. Now, it doesn't matter which direction is considered a negative, only that one is. So for example, this could be the positive and this could be the negative, or conversely, that could be the negative and that could be the positive. So remember, we indicate the direction of a quantity in physics with a plus or a minus. This means only vectors can be given a plus or a minus value. Now the only exception to this is temperature, but to be honest, we messed up that particular quantity when we considered its scaling. So it's also important to note you can work out the overall size of the vector by adding the two vectors up, but always considering the direction of those vectors. So to add these two vectors in this particular example, you would do overall vector is 5 plus minus 2, so the overall vector is 3 newtons. So to find the overall vector, you must add the vectors if they're in the same direction, but you subtract the vectors if they are acting in opposite directions. Now the name for the overall vector on an object can be called, if it's a force vector, the resultant force on the object. Now if an object has a resultant force acting on it, the object will accelerate. If an object has no resultant force acting on it, it will not accelerate. This means the object will stay at the same speed. Now the principle in physics which indicates that if there's no resultant force on an object will stay at the same speed is called inertia, and this concept is actually called Newton's first law of motion, or the first law of physics. It's a fundamental rule of our universe. But what happens if the vectors are not in completely opposite directions, like up and down? Well, to add any two vectors, regardless of their orientation to each other, we've got to draw a scale diagram. Now these accurately show the size and the direction of the overall vector, and remember, the overall vector can be called the resultant vector. Now resultant in physics means the overall or the observed, what you would see as the human. So you can't just add the two vectors to each other, because the resultant vector is the straight line distance from the start of the diagram to the finish of the diagram. So to actually draw this scale diagram, you've got to carry out the following. You've got to set a scale to your work. So it could be 1 square is equal to 1 newton. You then draw in the first vector with the correct length and the correct direction based on the scale that you have chosen. Now remember to draw the arrowhead of your vector as you do this. You then draw the second vector with the correct length and direction, but you've got to place the tail of this vector at the head of the previous vector. Now this indicates another name for a scale diagram, which is a head to tail diagram, because the head of one arrow is next to the tail of another arrow. So for example, we could say that vector 1 is 8 newtons and vector 2 is 4 newtons. Now this works on our scaling because we said 1 square equals 1 newton. So the vector 1 is 8 squares and vector 2 is 4 squares. Now the resultant vector is from the tail of vector 1 to the head of vector 2. Now remember, you should always be drawing in the arrowheads of your vectors as you draw them in. You then measure the length of the vector with the ruler and the angle with the protractor, and remember to convert the scale. So for example, if the resultant vector was 9 centimeters long and 1 centimeter equals 1 newton, your resultant vector would be 9 newtons. Now remember, when you give an angle which you've measured with your protractor, you've got to say where you started to measure the angle from, either the vertical or the horizontal. Now in most cases, it's easier to measure the angle from the vertical as opposed to from the horizontal. So to add vectors, you've got to draw a scale diagram. These diagrams accurately show the size and the direction of the overall vector. So to draw a scale diagram, you've got to set a scale to your work, draw the first vector with the correct length and direction, draw the second vector with the correct length and direction, placing the tail of this vector at the head of the previous vector. The resultant vector is then from the tail of vector 1 to the head of vector 2. You then measure the length of the vector with the ruler and the angle with the protractor, and remember to convert this with a scale. Now you might have realized that if the two vectors are at right angles to each other, you've drawn a right angled triangle. So this means in theory you could calculate the length of the resultant vector with Pythagorean theorem and calculate the angle of the vector with trigonometry. Now this method is actually an A-level method, so for GCSE exams you've got to do the scale diagram method, because the Pythagorean method can only be used if the two vectors are at right angles to each other. So what is this methodology? So you can calculate the length of the resultant vector with Pythagoras by saying the resultant vector squared is equal to the length of vector 1 squared plus the length of vector 2 squared. And we can work out the angle by saying tan of the angle is equal to vector 2 divided by vector 1, or opposite over adjacent, if you can remember that from trigonometry. So here's an example calculation of using this method. So you would say that the resultant vector squared in this case is 12 squared plus 8 squared, so it's 144 plus 64, which is 208. We then square root it to find the resultant vector, which is 14 newtons, which you'll notice is a lot smaller than if you just added the two numbers, because you've got to consider the direction of the arrows as well as their actual lengths. Then the tan of the angle is equal to vector 2 over vector 1. 8 over 12 is 0.67, so you do inverse tan of 0.67 and you get 34 degrees, and we've measured it from the vertical. So that is our value of our overall or resultant vector. Remember, we should always give our answers to the correct number sig figs with the correct units. So what have we learnt in today's lesson? Scalar quantities have a magnitude only. Vector quantities have a magnitude and an associated direction. A vector quantity may be represented by an arrow. The length of the arrow represents the magnitude, and the direction of the arrow shows the direction of the vector quantity. The number of forces acting on an object may be replaced by a single force that has the same effect as all the original forces acting together. This single force is called the resultant force. So you should be able to calculate the resultant force of two forces that act in a straight line. You should be able to describe examples of the forces acting on an isolated object or system, and then you should be able to use vector diagrams to illustrate the resolution of forces, equilibrium positions, situations, and determine the resultant of two forces to include magnitude and direction. So if you've been successful and learnt in today's lesson, you should be able to describe the differences between scalar and vector quantities, add vector and scalar quantities, and draw vector diagrams for vectors where the size and the direction of the arrow represents the size and the direction of the vector. So I hope you've enjoyed today's lesson on scalars and vectors, which is part of the forces topic in GCSE Separate Science Physics. Thank you very much for watching, and have a lovely day.